Here we go. We have a algorithm named Kosaraju algorithm. So it is used to find strongly connected component. What is a strongly connected component? It means starting from a vertex, we can visit to all the other vertices. From one we can visit to other vertices. From two we can visit other vertex. From three we can visit other vertex. From four we cannot visit this vertex. So this component is a strongly connected component. We can visit from a vertex to every single vertex in a particular component. So from this we can visit to other vertex, from this we can visit to other vertex, from this we can visit to other vertex, from 7 we cannot visit. So this is a separate component. So this from we can visit. So this is a separate component. We got three separate strongly connected component. So let's look at the problem statement. We got strongly connected. So you have given a directed graph and we need to find strongly connected component. So in this we got three strongly connected components, 0, 1, 2, then 3, then 4. So we have three separate components, three strongly connected component. In this we have one strongly connected component. So let's try to understand about Kosaraju algorithm. So in the Kosaraju algorithm we do a DFS kind of topological sort. In topological sort, the first thing, the first criteria is the graph has to be directed acyclic graph. But here we have a cyclic graph. So it's kind of a topological sort but not exactly a topological sort. We start from a vertex, then what we'll do, we start from a vertex, we add we add into the recursive stack, we visit to its neighbor, okay, then we visit to its neighbor, okay, then its neighbor is already visited, then we will pop out and store it. That's what we do in topological sort. Then we go 2, from 2 there's a path to 4, to path 5, to path 8, to path 7. From 7 we cannot reach ahead, so just remove 7 and store it here. Then from 8 we can also reach 9. 9 neighbor is already visited, just remove 9 and add it here. From 8 we have visited all the other vertex. From 8 we have visited, so add it here. Then from 5 there's a path to 6. So from after 6 there's a path but it is already visited, so we have to pop out. Then from 5 there is no other vertex. From 4, 2 and 1 there is no other vertex. Then we go to this, we store it into a list. After that the next step is to edges reverse the edges. So Kosaraju says if we have a strongly connected component, so let's say this component, and if I reverse all the edges, it is still a strongly connected component, as you can see. So if we attach 4 here and 4 is here, so this is a separate component, this is a separate component, then this is a separate component, this is a separate component. So we have two strongly connected component. If we reverse the edges, we still have a strongly connected component. So let's reverse the edges and write it here. So we got 1, then 2, then 3, then we got 4, 6, 5, we got 8, 9, and we got 7. Then what's the starting point? What's the starting point? We got 3. So we will start from, what we'll do. So now let's continue. What we got, we have reversed the edges, and in topological sort, what we do is whenever we got whenever we remove a node, we don't usually print it. It's in reverse order. So there's a edge from U to V. So U So which means 1 must come before 2. 1 must come before 2. So whenever we got a node, we usually add it into a stack. So let's add it into a stack. So we go to this, and we don't usually print it, we just add into a stack according to topological sort. So now let's use this. We go to this. Now the first value that we have is 1. So we will start our loop from 1 and visit all the vertices. So starting from 1, we will visit this, we will visit this, we will visit this. So 1 that we removed from the stack, one that we removed from the stack is initially unvisited, which means there's a component that we have not discovered. So component is initially 1, then when we popped a value from stack, we have to increment. So then we got 2. 2 is already visited, this component is already discovered, so we don't need to update our counter. Then we got 4. So from 4, let's start from 4. From 4 I will visit this, then this, then this. So we again have to increment the counter. One component is this and one component is this. Then we got 5. 5 is already visited, 6 is already visited, 8 is already visited, 9 is already visited. Then we got 7. We will mark it 7. Then we got 3. Actually it is not 3, I think it is 8. Yeah, 3. We got 3. So 3 is already visited. And I missed to update my counter. So that's how this algorithm will work. After reversing it, just get a value from topological sorting stack, then just apply a DFS again. So I will use this, I will use DFS, the same DFS for these two traversal, and for initially I need to add the nodes into a stack, and here I don't need to add. So I will just pass a parameter. Is this a first DFS? If this is yes, then I will add. If this is not a first DFS, I will not add. So Kosaraju algorithm is very straightforward. Let's look at the coding part. We got stack, topological sort stack. Then this is not a topological sort because this is not a directed acyclic graph. This is a cyclic graph. Then we have visited. If a node is not visited, so then just apply DFS by passing adjacency list, starting point, visited array, and true, which means this is my first DFS. So just mark it, traverse the neighbor. If neighbor unvisited, then only traverse. So this is, if this is my first DFS, add the node into a stack. Then reverse, we need to transpose it. So we need to first build our transpose list. Then we have a edge from j to I. So we have transpose it. Then I will just reinitialize my visited array for the same DFS call. So I need to again reinitialize it. Then we need an answer to return how many strongly connected components are there. While we have elements in the stack, just remove it. If this is unvisited, then increment your counter and visit all the connected nodes, and I will pass false. False for telling me false for telling the function that this is not first DFS, this is a second DFS. Then that's enough. This code will work. Let's give it a try, and let's talk about time and space complexity. So we are visiting a node and we are traversing it. Then the space complexity will be, let's look at the expected space complexity. Before that, let's wait for it to submit. And yeah, it is submitted fine. And what we got, yeah, space complexity. So as I expected, space complexity is v plus e. For this reversal we have v plus e. And we are visiting a particular node only once. Then here we are also visiting a particular node only once. For space, we have built this transpose, so it will be v plus e. And now it's time to wrap up. I hope you have learned something new. Code is provided in the description box. Thank you all for watching.